Good afternoon. Just looking at what we have in the test to review handout set, and we have just going back throughout. We have had working with functions, and we have with the first set of items. Okay, now we're looking at the attainment of values of functions for specified inputs, as well as trying to find out the domain of a given function. And we have, in the case of the first item, okay, so we got a radical function whereupon we have f of x is equal to the square root of x plus 11. Okay, so we have for this item, okay, so we have f of x equal to the square root of x plus 11. And looking at for what we have in the first part. Okay, so we're looking at finding out what the value of f at 25 is. Okay, so for what we have in terms of the xy coordinate system, okay, now we got the x value to be at 25, and we have f at 25. That's going to be in reference to the y value whenever x is set to 25, and finding out what y is going to be. Okay, so we have with the function, okay, have y is equal to f of x is equal to the square root of the input plus 11, and with x at 25, okay, so we have that y is equal to f of 25, which is equal to the square root of 25 plus 11. And 25 plus 11 is 36. And, okay, so we have with the square root of 36, again, we have with the principal square root rule, again, the square root of an expression cannot lower to a negative constant. Okay, so we have with 36, now there are two numbers that will square into 36, but we're interested in only the positive value. So the square root of 36 in this case comes out to 6. Okay, so when x is 25, we have that y is equal to 6. All right, and we have with the next input value, okay, we have in part B, we're looking at the value of the function whenever x is at negative 7. Okay? And so with what we have here, with x at negative 7, so we have that f of negative 7 is equal to the square root, and we have of negative 7 plus 11. Negative 7 plus 11 is 4. And we have the square root of 4, and 4 being a perfect square value, and its square root is going to be positive 2. All right. Now, in the case of what we have in the third part, we're looking for the domain of f of x. All right, now for the domain, okay, we're looking at all the values of x, okay, whereby, okay, f of x is going to be a real defined value. And with the nature of the function, okay, now we have an even root radical. In this case, we have a square root, and this is going to signify that whatever we have for x plus 11, x plus 11 cannot be negative. Okay, now since the radical function is given in direct terms, now we can have the square root of 0 as well as the square root of a positive. So in this case, x plus 11 could be 0 or positive. And looking at trying to find out what set of values will be allowed for x, okay, we can ensure that x plus 11 is greater than or equal to 0. And if x plus 11 is greater than or equal to 0, and getting x by itself. Okay, so subtracting x from both sides. Okay, we want to have the x is greater than or equal to negative 11. Okay, and so just looking at what we have in specifying the domain. Okay, and now the graphing is optional, but just looking at it from a visual perspective. So we have the value of interest at the immediate moment, okay, to be negative 11. Okay, now the statement has that x is greater than or equal to negative 11. So with the equal sign, negative 11 is included. So on the number line, okay, we have a solid point on negative 11, and the rest of the values of x will be greater. And so we're going to have a ray going out continuously to the right. Okay. And you can see I have increasing and heading out in the direction of infinity. Okay, so for the domain of what we have for this particular radical function, okay, we're going from and including negative 11 all the way out to positive infinity. Okay, now for what we have in the case of the next function. Okay, so this time, okay, we have f of x is equal to x minus 3 all over the square root of x minus 4, and we're looking at the values of y whenever x is at 5 and also whenever x is at 9, and just like number 1c, number 2c is asking for the domain. Okay, so we have in problem number 2, okay, so we have f of x is equal to x minus 3 all over the square root of x minus 4. And for what we have in the case of part A, again, the first x value, okay, we have at 5. And so transitioning from x to 5, okay, so we have in the statement x minus 3 becomes 5 minus 3. And in the denominator, okay, we have the square root of 5 minus 4. So you have the 5 minus 3 is 2. And we have the square root of 5 minus 4 is going to be the square root of 1. And again, square root of a positive value is going to be a positive only. So for f of 5, okay, this narrows down to 2 over 1, which is equal to 2. Now, for what we have in the case of part B, okay, so now we're going from x equals 5 to x is equal to 9. And taking what we have upon substituting, okay, so x minus 3, we have at 9 minus 3. For the square root of x minus 4, okay, we have the square root of 9 minus 4. Now in exact terms, you can express the result in either of two ways. Okay, so we got 9 minus 3 is 6. And we have all over the square root of 5. Okay, now you don't absolutely have to do this, but you can also rationalize the denominator. And what I mean by this is that you can have the radical removed from the denominator. If I multiply by 1 in the form of the denominator all over itself, in this case you have the square root of 5 over itself. Can you do that like in the case for this type radical if we had the number to not be a perfect square value? Okay, so in this case, if I take this approach, I have 6 times okay, the square root of 5. And the square root of 5 times itself is going to be the square root of 25, which lowers to 5. So you can express the answer in either of two ways. So either display is fine. Now, for what we have in the case of the domain, okay, so we have x to appear twice in the expression. And in terms of any restrictions, okay, this will come from the x minus 4 portion. Okay, and we have x minus 4 as playing a bit of a dual role. One of which is, okay, we have inside the radical, which is in the form of the square root. And again, with even root radicals, okay, the expression cannot be negative. And because x minus 4 is also in the denominator, okay, so in this case, right, we have the x minus 4 cannot be equal to 0. So you have can't be negative, can't be 0. So that means that out of the characteristics or categories, okay, only we can allow x minus 4 to be positive. And for what we have as the setup for the defining inequality, okay, so you have the x minus 4 must be greater than 0, and specifying what we have for x. So adding 4 to both sides. So we're going to have the x is greater than 4. Again, just for the value of interest, okay, we have 4, which is not part of the solution. Okay, so we have with 4 not included, we have an open circle as opposed to what we had earlier with negative 11 in the first problem when we had the equal sign signifying that negative 11 is part of the solution set for x. But here with 4 not included, again, we have an open circle. And from this, okay, we have a ray going out to the right and moving continuously in the direction of infinity. And so for the domain of what we have here, so you have going past 4 on out to infinity. Again, since 4 is not part of the solution, and also since infinities are boundless, okay, we have the exclusive use of parentheses for the notation. All right, now for what we have in the next set of items, and we have with problem number 3. Okay, so going back to parallel and perpendicular lines. And we're looking at determining the equations, okay, in the slope-intercept form. That is, the y is equal to mx plus b. And for what we have here, okay, first case we're looking at where the line is going to be parallel to 2x plus y is equal to 4, and simultaneously be passing through 3, 3. All right, so we have for this item, okay, so we have for the given line, again, that is defined by the equation in the standard form, okay, whereupon we have 2x plus y is equal to 4. And want to know what the slope of this line is, just to be able to attain the equation in the slope-intercept form of the parallel line. Okay, so we have for the given line, okay, so you have 2x plus y is equal to 4. And rewriting this in the slope-intercept form, and we have upon getting y by itself, okay, so if I take 2x away from both sides, okay, so I have y is equal to negative 2x plus 4. Okay, and so with the slope-intercept translation, okay, for the given line, okay, so I have that the slope m is equal to 2. Okay, now looking for the equation of the parallel line in the slope-intercept form, again, parallel lines are going to have the same slope. So that slope is also negative 2. And the parallel line is going to pass through 3, 3. Okay. And since we have the 3 to repeat, just going to do a little bit of color coordinating just to draw out how those 3's are going to play out. Okay. So we have in the case of the formation of the point slope equation pathway to get to the slope intercept, again we have y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. And we have upon substituting, okay, so for y minus y of 1, okay, so we have y minus 3 is equal to the slope m, okay, which is negative 2, times the quantity of x minus x of 1, so that's going to be x minus 3. Okay, so this is the point slope equation, but I'm looking for the slope intercept. Okay, so upon continuing, okay, so you got y minus 3, and now I can distribute negative 2 over the quantity of x minus 3. So this will become negative 2x plus 6. And getting the y term by itself, okay, so we have upon adding 3, let's see, it should be 2x plus 6. Okay, so for what we have in the follow through, okay, so we're going to have that y is equal to negative 2x, and we have with 6 plus 3, okay, this will come out to 9. Okay, so this will be the slope-intercept equation. Okay, notice I had created a little bit of a misstep. Okay, and whenever you come to the slope-intercept, you can always go back and check. Again, the slope of what we have here for the slope intercept form of this equation. Okay, so you got the slope at -2, and to see if the line represented by this equation actually passes through 3, 3, and this will be your quick litmus test. Okay, so we have y at 3, and I want the right hand side of the equation to also be at 3. So you got 3 on the left, and to the right I have -2 times 3, which is -6, and in turn -6 plus 9 is also at 3. 3 is equal to 3. All right, now in the case of what we have with the fourth item, okay, so we're now looking for a perpendicular line, and we have the given line determined, or I should say represented by the equation 2x minus y is equal to 4, and we're looking at the perpendicular line to pass through 2, 7. Okay, and so we have for this item, okay, so 2x minus y is equal to 4, and I want to find out, okay, just what the slope of this line is going to be. And if I rewrite this equation in terms of the slope-intercept layout, I'll be able to get to the slope. Okay, so if I isolate the y term, which I have right now at -y, okay, so I have, upon taking 2x away from both sides, okay, so I have -y is equal to -2x plus 4. And if I multiply everything by -1, in this case multiplying both sides of the equation by 1, -1. So in effect, I'm making the positive terms negative and vice versa. Okay, so in this case, we're going to have that y is going to be equal to 2x minus 4. All right, so we have with the given line, okay, we have that the slope m is equal to 2. Okay, now we're looking for the equation of the perpendicular line described. Let's see. Okay, so you have with the perpendicular line. Okay, now again, the slope of the given line, okay, we have at 2. Okay, now perpendicular lines will not have the same slope. Instead, okay, the slopes of perpendicular lines will have values that will be opposite sign reciprocals. So I'm going from a positive 2 to a negative reciprocal of 2, and in this case I'm going to have -1/2. And again, just to restate again, for the product of the slope values of lines running perpendicular. Okay, so first line given, we have 2. And again, for the slope of the perpendicular, we have -1/2. This is just a double check. Okay, so the product, we have -2/2. And -2/2 is equal to -1. Now, the point through which the perpendicular line is going to pass, Okay, that's going to run through 2, 7. Okay, and again, just creating the point slope formula backdrop. Okay, so you have y minus y01 is equal to the slope m times the quantity of x minus x01. So for y minus y01, okay, so you have y minus 7. And we have with the slope m, okay, so you have a negative 1/2. And you have times the quantity of x minus 2. So this is your point slope formula. Now for the slope intercept, so I'm looking at distribution. And so I have y minus 7 to the right. And we have negative 1/2 over x. So I have minus 1/2 of x. And for negative 1/2 times negative 2, okay, that's going to be positive 2/2, or in this case, positive 1. And solving for y, after the distribution, okay, so I'm going to add 7 to both ends. And for what I'm going to have here, okay, it's going to be y is equal to negative 1/2 of x, followed by the addition of 8. And you can go back and check. Okay, so you have y at 7. Left-hand side of the equation is at 7, and I want the right-hand side to be as well. So with x at 2, we got negative 1/2 of 2 is negative 1. And in turn, negative 1 plus 8 is also equal to 7. Now, for what we have in the case of crossing over, and we have in number 5, okay, so we're going back to looking at domain, okay, and with 5 and 6, okay, we have rational functions. And for what we have in number 5, okay, so you have f of x is equal to 2x plus 7 and we have all over x squared plus 4x plus 3 okay, and again for a rational function, okay, we cannot have a zero-valued denominator. Okay, so the restriction here, now we got a couple of x expressions. Now 2x plus 7 can be 0 as long as it does not create a zero denominator. So the restriction lies with the denominator. Okay, so with the denominator x squared plus 4x plus 3. Okay, so this trinomial cannot be 0. And pinpointing, okay, just what values of x will be excluded from the domain. So we have with this expression, which is factorable. Okay, so for x squared plus 4x plus 3, okay, so this will factor out to the quantity of x plus 3 as well as the quantity of x plus 1 okay, so you have the product cannot be 0, and so neither can the expressions. So we have that if x plus 3 cannot be 0, we have the x cannot be negative 3, and if x plus 1 cannot be 0, we have the x cannot be negative 1. So in looking at what we have here, okay, so we got the excluded values with negative 3 and negative 1. and with -3 and -1 left out. Okay, so we can, in graphing terms, okay, just symbolize the exclusions with the open circles. But everything else, in between the values as well as outside of them, left and right, will be in the domain. Okay, so you have at the extreme ends, okay, so you have between -infinity and -3, then we have between -3 and -1, then we have those values going past -1 on out to infinity. Okay, so for the domain that we have here, okay, so we have going past -infinity and approaching, but not including -3. We have also, okay, bypassing -3, so you had in the domain those values between but not including -3 and -1. Then we have for the rest of the set, we have those values of x greater than -1, and the interval notation we have with parentheses surrounding -1 and infinity. Okay, now for what we have in the case number 6, so I have 2x minus 1 all over x squared minus 4. Okay, so I have 2x minus 1 over x squared minus 4. Okay, again, partial history repeating. Okay, again, we have a rational function. And again, the restriction is going to be that the denominator cannot be equal to 0. So we have x squared minus 4 cannot be equal to 0. So for what we have here, okay, so you have x squared minus 4 we have with the difference of squares. So one binomial will be of addition and the other will be subtraction of the same value. Okay, so we have x plus 2 and x minus 2. And once again, we have neither factor can be 0 in value. Okay, so here, if x plus 2 cannot be 0, okay, so we have that x cannot be -2. And we have if x minus 2 cannot be 0, we have that x cannot be at 2. Okay, so we have, once again, two exclusions from the domain. Okay, and this time the numbers left out, we have a negative and positive 2. Again, just applying the circles here. Again, we have the separate modes of activity. All right, so you have the domain, okay, have broken up into 3 separate subintervals. Okay, and for the least of the values have between -infinity and, but not including -2. So again, that's for those values of x less than negative 2. Then you have those values of x such that negative 2 is less than x is less than 2. You have for the last of the subintervals, okay, you have in reference to those values of x greater than 2. And since neither negative nor positive 2 will be included in the solution set, we have the use of parentheses throughout as the grouping symbols. Now, looking at what we have concerning going back, okay, to the slope-intercept equation. Now we have with number 7, okay, so we're going back to not just the slope-intercept equation, but just kind of a prelude to this, okay. So we are now, instead of having the slope available right away, we have 2 points given through which the line is going to pass, and we have to find out what the slope is going to be, as well as what components we have that will enable us to get to the slope-intercept equation. Okay, so we have for problem number 7, so with the line, so it's going to pass through negative 1, negative 3, as well as 3, 5. Okay. And okay, so I had to find the slope of the line that runs through these ordered pairs. Again, we have with the slope formula. Okay, so you have y of 2 minus y of 1. And we have all over x of 2 minus x of 1. Okay, and okay, before we start working with the formula right away, we can go ahead and identify, okay, just what the first and second x and y value sets will be. And again, all ordered pairs are the form xy. Okay, and since negative 1, negative 3 is given first, we'll say that negative 1 will be the first x and negative 3 will be the first y. And with 3, 5 provided subsequently, we can say that x of 2 is 3 and y of 2 is at 5. And so after identifying the first and second x and y values, before working with the formula, we can go ahead and have things set up whereupon we can substitute right away. Okay, so for y of 2 minus y of 1, okay, so y of 2 is at 5. You have minus y of 1, so you have subtracting negative 3. And all over x of 2 minus x of 1, so x of 2 is at 3. And we have subtracting negative 1. Okay, so you have in both the numerator and denominator, I have the subtraction of negatives. Okay, so 5 plus 3 is 8. And 3 plus 1 is 4. And 8 over 4, okay, is equal to 2. Okay. Okay, now for what we have, okay, now for the creation of the slope-intercept formula. Okay, and for what we've got, okay, again, you can choose either of these ordered pairs, okay, in creating the point slope setup, okay. Okay, so I can choose either of these order pairs to set things up. But again, I'm still looking at the slope-intercept equation. Okay, so going back to what we have, again, we have y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. Okay, and again, you can choose either -1, -3, or 3, 5. And you might go with -1, -3 since that was the first ordered pair. However, if you don't care to work with negatives any more than you have to, especially when subtracting negatives, you can go with 3, 5. Again, there's no one right choice. Okay, either one works. And so we have now the tools at hand. So we have for 3, okay, this will be in reference to x of 1. And we have with 5, okay, this will be for y of 1. And again, we had the slope earlier to be determined at 2. So for what we have now, okay, we have upon substituting, so we have for y minus y of 1, so you have y minus 5. That is equal to the slope m, which we have at 2. We have times the quantity of x minus 3. So this is the point slope formula. And now putting this in terms of the slope intercept. Okay, so if I look at distributing, so for y minus 5, we have is equal to 2 times the quantity of x minus 3. So this will be 2x minus 6. And we have getting y by itself. Okay, so adding 5 to both ends. So you have that y is equal to 2x minus 1. Okay. And you can go back and check. Okay, so you have 3, 5. So if we were to test out 3, 5. So y at 5, left-hand side of the equation is at 5. And with x at 3, we have 2 times 3 is 6. 6 minus 1 is 5. Left and right-hand side of the equation come out to 5. And I can also test out -1, -3. So with y at -3 and x at -1, left-hand side of the equation is going to be -3, and I want the right-hand side to be as well. So we got -3 is equal to, and 2 times -1 is -2, and -2 minus 1 is also -3. Okay, now in looking at functions and functional values and expressions, now we have in the case problem number 8, and we have a given function, okay, whereupon we had that f of x is equal to -x squared minus x plus 4. Again, f of x is a functional notation for what we otherwise say is going to be y. And we're looking at the y values, say when x is at 3, and also when x is at -2. And also in terms of variable inputs, we can see what the input of x plus 4 is going to lead up to for this particular function. Okay, and so we have with number 8, okay, so we got so we have that f of x is equal to the negative of x squared minus x followed by the addition of 4. Okay, and so with the first value, okay, so you have f of 3. And let me mention something here. Okay, so you got -x squared minus x plus 4. Now -x squared, okay, you're looking at the opposite sign of x squared, not the square of -x. If I squared -x, I would need -x inside the parentheses. So let me just kind of mention this. So just for what we have in context. So you're looking at -1 times x squared minus x plus 4. Okay, now with 3, so I'm looking at the negative of the square of 3 I got -3 plus 4. Okay, so for what I have, at least in context, okay, so 3 squared is 9, but taking the opposite sign of this. So we have -9 minus 3. -9 minus 3 is -12. In turn, -12 plus 4 is equal to -8. Okay, now for the next input, okay, so that was with -2. Okay, now for f of -2, so we'll be looking at the negative. Again, so you have -1 times the square of -2. I have minus -2 followed by the addition of 4. Okay, now, let me mention, okay, so we have with the square of -2, just the square of -2, okay, so that would be 4, but I'm still taking the opposite sign of 4. So I got -4, subtracting -2, so this will be +2. So you have -4 plus 2 is -2. And in turn, we have -2 plus 4 comes out to 2. Okay. Now, in the case of going from constants to variable inputs. Okay. Now we got for the binomial. Okay, we have f of x plus 4. And operating in line with what we had to define f. So again, you're looking at the opposite sign of the square of the input. So now we're looking at the opposite sign of the square of x plus 4. Again, have minus the input, so you're looking at subtracting all of x plus 4. And you have followed by the addition of 4. Okay, so, and what we can do, let me tell you what, on the side, okay, so if I go ahead and square out x plus 4, so for the square of x plus 4, so I'm looking at x plus 4 times itself. Okay, and just foiling out, so I have x squared plus 4x plus 4x plus 16. And again, so combining the middle terms. Okay, so I have x squared plus 8x plus 16. Okay, so I'll be taking the opposite sign of this expression. Okay, so just crossing over. So for the opposite sign of the square of x plus 4, and we can go ahead and distribute the subtraction over all of x plus 4. So we have a negative x. And also have minus 4. And just looking at distributing. Okay, so got the negative sign. So all these positive terms will become negative. So got negative x squared minus 8x, you got minus 16, and you got minus x. Now, you can go ahead and cancel out the negative and positive 4. Okay. Okay. And just accumulating, okay, the like terms. Okay, so we got negative x squared. And we have a negative 8x and a negative x among the first order terms. So those will combine to negative 9x. And again, we have negative 16, and we have minus 4 plus 4 will cancel out. So the negative 16 is going to be the resulting constant. Okay, so for f of x plus 4, okay, we end up with 3 negative terms with minus x squared, minus 9x, and also minus 16. All right, now for what we have in the next group, okay, and we have crossing over to working with piecewise defined functions. And we have for number 9, okay, so we have you have f of x, okay, partitioned into 3 separate sections, and looking at the various values, okay, for the inputs specified. Okay, so we have again for f of x, okay, we have negative 3 if x is less than 4. F of x is equal to the absolute value of x if x is such that 4 is less than or equal to x, which in turn is less than 8. And then we have that f of x is equal to 7 should x be greater than or equal to 8. All right, so we have with the input value at negative 4. First of all, locating where negative 4 as an x value belongs among the inequalities. And negative 4, right away, negative 4 is the value that is less than 4. And for any input that is less than 4, the y value is just going to be equal to negative 3. Okay, so we have f of negative 4 is equal to negative 3. All right. And for what we have in the case of the next input value, okay, so that is going to be at 1/2. Okay, now you have a positive 1/2 for the input as opposed to a negative 4. Now 1/2, just like negative 4, is also another term that is less than 4. And since 1/2 is less than 4, just like negative 4, the y value is still going to be fixed at negative 3. So just as f of negative 4 is equal to negative 3, f of 1/2 is likewise. Okay, now for the input at 6. Okay, so in terms of where 6 belongs, okay, so 6 is not less than 4. So first inequality does not apply. And to see if the next one does, 4 is less than or equal to 6. Well, 4 is less than 6, so that part is true. In turn, we have that 6 is less than 8, also true. So the second of the inequality statements will in this particular case, will apply. Okay, so you have 4 is less than or equal to 6, which in turn is less than 8. So for any input x that belongs to the second of the inequality statements, we're going to take the absolute value part of the function. Okay, so in this case, we have that f of 6 is going to be equal to the absolute value of 6. And specifying numerically. So the absolute value of 6 is equal to 6. Okay. Okay, so you have that f of 6 is equal to 6. And for now, the absolute value of a number, can never be negative. I know what you're probably thinking of. I know what you're saying. It's like the absolute values of what numbers would be 6. It would be like 6 and negative 6. But I'm looking at just the absolute value of 6. Yeah, so if you have the absolute value of a 0 is 0. Absolute value of a negative is still going to be a positive. Absolute value of a positive is going to be a positive. Okay. And I know what you're saying. It's, so if you have like absolute value of x is equal to 6, like x would be plus or minus 6. But for what we're kind of looking at here, say if I have like x is equal to the absolute value of 6. Absolute value of 6 comes out to 6. Yeah, so if the problem had been like absolute value of what numbers is equal to 6, you would have positive and negative 6. But if I'm looking at just the absolute value of 6, that comes out to 6. All right. Now, in the case of what we have for f of 15, okay, and for the input value of 15, okay, we have 15, okay, it's not less than 4, it's not between 4 and 8, but it is a value that is greater than 8, so we're going to have that 15 is greater than or equal to 8. And so for any input that is 8 or higher, okay, you're going to have just that y is equal to 7. Okay, so you're going to have the f of 15 is equal to 7. Okay, we have, with number 10, we have f of x is equal to 4x minus 3 for values of x less than 0. And we have the f of x is equal to x squared minus 1 for values of x such that 0 is less than or equal to x is less than 5. And we have that f of x is equal to 2x plus 1 for those values of x greater than or equal to 5. Okay, so we have for this setup, and so I'm going to kind of minimize what we have here. So for number 10, okay, so we have looking at the input value at negative 3, okay, and any value that is negative automatically is less than 0. Okay, and so for f of negative 3, in terms of what to do with negative 3, okay, so we're going to have the 4x minus 3 treatment. So f of negative 3, okay, this will be 4 times negative 3 followed by the subtraction of 3. So you got 4 times negative 3 is negative 12. And negative 12 minus 3 comes out to negative 15. Okay, so we have a numerical result. So we have f of negative 3 is equal to negative 15. Now, for the next of the inputs, okay, so we have the decimal value, okay, with 0.6, okay, and looking at which of the functions will apply is going to be contingent upon where 0.6 as an input belongs. Okay, so 0.6 is positive, so it cannot be less than 0. And then we have with the next inequality statement, now we got 0 is less than or equal to 0.6, so that rings true with the less than part. In turn, 0.6 is less than 5. That is also true. So we apply the x squared minus 1 portion. Okay, so so for what we have in the setup, okay, so we got 0 is less than or equal to 0.6, which is less than 5. And again, we're applying the x squared minus 1 treatment. Okay. In this case, I have 0.6 squared minus 1, and the square root of 0.6. Okay, so this would be 0.36. So we're coming out to an even smaller value and taking away 1. Okay, so you have negative 0.64. Okay. So it's going to follow that f of 0.6 is equal to negative 0.64. Now, for what we have in the case of f, 4.9, okay, now 4.9 is substantially larger than 0.6, okay, but like 0.6, that value also belongs in the second inequality, since it also happens to be less than 5. Okay, so that number is also going to go through the x squared minus 1 treatment. So 0 is less than or equal to 4.9, which in turn is going to be less than 5. Okay, so looking at what we have with the numbers, so you have f of 4.9. Okay, so this would be 4.9 squared minus 1. 4.9 squared would be 4.9 times itself. So you have it 24.01. And taking 1 away from both sides, so we have it 23.01. So we have the f of 4.9 is equal to 23.01. And we have in the case of, let's see, the remaining input, so we have f of 5. Okay, so that number appears twice among the inequalities. Now for 5, now 0 is less than in the less than or equal to 5 part. However, 5 cannot be less than itself, so thanks to the second half requirement, the second statement cannot apply for 5. But for the last statements, we have that trying to say that x is greater than or equal to 5 when x is 5. Now 5 cannot be greater than itself, but it is equal to itself. So the equal to part, okay, makes this last inequality statement applicable for the input value of 5. So we're now going to use the 2x plus 1 portion of the piecewise defined function. Okay. So for f of 5, okay, so this will come out to 2 times 5. Plus 1, 2 times 5 is 10. Plus 1 is equal to 11. Okay, so we have the f of 5 is equal to 11. Okay, now in the crossover, okay, to what we have regarding operations between functions. Okay, and we have a couple of linear functions, okay, and it says to determine, okay, the sum, difference, product, and quotient functions as well as their domain, and you have followed by the compositions between f of x and g of x. Okay, so right now, okay, looking at the numbers 11 through 14 for the terms that result, as well as the domain. Okay, so right now we have in number 11. Okay. Let's see, again, that was f of x equal to 2x minus 12. And we have that g of x is equal to x plus 14. Okay, now for what we have in the case of first item, okay, so just for number 11, and we'll get to the domains at the end. Okay, so for f plus g of x, all right, so you have f of x plus g of x, okay, and just specifying, okay, what we have for f of x and g of x. Okay, so I'm just going to use parentheses, okay, to separate right now f of x from g of x. And just looking at what we have, removing the parentheses. Okay, so I got 2x minus 12. And we have x plus 14 to follow. Okay, and combining, okay, so you have 2x plus x is going to make 3x. And negative 12 plus 14 comes out to positive 2. And we'll get to the domain of this operational function in just a moment. Okay, now for what we have for the difference function, okay, so I'm still working with f of x and g of x. Okay, and this time around for the difference function, we're looking at the difference between f of x and g of x. So again, we have f of x, we have at 2x minus 12. G of x we have with x plus 14. Now, if you notice, okay, we have with the difference once we remove the parentheses. So we still have 2x minus 12. But now for the subtraction of g of x, okay, we're going to have the subtraction of x as well as 14. So this will translate to minus x and also minus 14. And so we have 2x minus x becomes x, and negative 12 minus 14 becomes minus 26. As for what we have in the case of the product function, okay, for f times g of x, okay, so we got f of x times g of x. Okay, so you have 2x minus 12. You have times the quantity of x plus 14. And just taking the FOIL method, so you got 2x times x. So this will be 2x squared. And we got 2x times 14. So it'll be a 28x. We have minus 12x. And for negative 12 times 14, have a highly negative value with minus 168. And combining the first order x terms, so we come out to 2x squared plus 16x minus 168. Now, again, the sum, difference, and product functions will have the same domain, okay? And their domain will be on the basis of the exclusions combined from the immediate functions involved, okay? And I'm just going to mention, okay, so we have with f of x and g of x. Okay. Now for f of x alone, okay, you got 2x minus 12 g of x. You have x plus 14. Guess what? You don't have any fraction or even root radical. Okay, just for f of x, okay, you're going to have, for the domain, you're going to have the set of all real numbers. And the same thing is going to apply to g of x. Okay, so g of x, okay, again, we have no restriction, and its domain is also going to be the set of all real numbers, okay. And since we have that the sum, difference, and product functions don't have any restrictions here between f of x and g of x, we have the same domains throughout. So for the sum, difference, and product functions, we're going to have the set of all real numbers. Okay, now for what we have in terms of the quotient function, again, there's the potential that the domain can be quite, or can have an offsetting difference, okay, and that's because with the setup in the quotient function, we cannot have the denominator to be 0. So for what we have in the case of 14, we got with the quotient function. So we have f over g of x so we got f of x over g of x. Okay, and again, just putting in, okay, so f of x, we have it 2x minus 12. And for g of x, okay, so I have x plus 14. And between the numerator and denominator, okay, there is, the greatest common factor is only 1, so there's nothing special to factor out that will be common to both the numerator and denominator. So just a substitution in this case leads to our simplified expression. Now, for the domain, okay, we now have a restriction, and that's because g of x did not have a restriction before because it was in direct terms, but now that we have it in inverted terms, that is where g of x is at the bottom, we now have it that x plus 14 cannot be equal to 0. And if x plus 14 cannot be 0, we're going to have that x cannot be negative 14. Okay, so for the exclusion, okay, we have only negative 14, and everything else from the real number system, okay, will be in the domain. So for the domain of the quotient function, okay, we have broken up into two separate interval sections. Okay, at the lower end we have where those values of x less than -14, so we have parentheses around -infinity and -14. And for the other section, for those values of x greater than -14, so you have -14 and infinity, and again reapplying parentheses around those values. Okay, now for what we have in 15 and 16, again, we're still working with the same individual functions, okay, but now with compositions. Okay, we had the domain requirements to be playing by a different set of rules, not opposing rules, but just a different set, not totally in line with the previous 4 operations. Okay, so again, we have with these functions, if we're looking at the composition, where we have f composed with g of x okay, so for f composed with g of x, so we're now looking at f of g of x. All right, so you have g of x is the input function, and the output will be in line with f of x. Okay, so you got, okay, so for f of x, f of the input is equal to 2 times the input minus 12. Okay, so we have 2 times g of x minus 12. And applying, okay, just specifically what defines g of x. So we're now going to have 2 times x plus 14, or 2 times all of x plus 14. And we have followed by the subtraction of 12, and just carrying over. So we have 2x plus 28 minus 12, and we have, in the case of the output, so this will become 2x plus 16. Okay, now for the determination of the domain, okay, so you're looking at keeping the input as well as the composition itself defined. Okay, so you have the input so the input is equal to g of x, okay, which is going to be at x plus 14. Again, input has no restrictions. And with the output, you got 2x plus 16. And since you don't have a fraction or an even root radical or anything that creates an exclusion from the real number system, okay, we also have no restrictions. And so between the input and the output, okay, we have no restrictions at all. Okay, so we have for the domain of the composition whereupon f is composed with g of x, can we have the set of all real numbers. Okay, and for what we have in the case of taking the reverse order, okay, so going from f composed with g of x to g composed with f of x. Okay, so now I have g of f of x. Okay, so it's trading places in a sense between what's the input and what's the output. So the output is in line with g, okay, where g of the input again is defined as the input plus 14. Okay. So for g of f of x, okay, so f of x is the input. So you have f of x plus 14, and now specifying the variable expression that defines f of x, we have 2x minus 12. Okay, once you take the parentheses out, you have still 2x, and the constants will be combined, whereupon negative 12 plus 14 comes out to positive 2. Okay, so in terms of the domain, okay, so just looking for any possible restrictions. And again, so you have for the input, again, we have at f of x, which you have at 2x minus 12. And again, so you have a direct variable expression, no fraction or even root radical, so you have no restrictions. And we have, in the case of the output, we have is equal to 2x plus 2. Okay, so you have no restrictions. So again, we have between the input and the output. Okay, so you have no restrictions at all. And so for, once again, the domain is going to be the set of all real numbers. Okay, with the function f of x, okay, so you have x minus 1 all over x squared minus 4x plus 3. And again, so for this rational function, can we have the restriction to be that the denominator cannot be 0 in value. Okay, so for x squared minus 4x plus 3, okay, since this cannot be 0, okay, we have with our factors, you see we have x minus 3. And x minus 1, okay, neither of which can be 0. So if x minus 3 cannot equal 0, okay, so we have that x cannot be equal to 3. And if x minus 1 cannot equal 0, okay, so I have that x cannot be equal to 1. So just looking at what we have here. Okay, so like just in case if you got your zeros not in increasing order, strictly speaking, so just identifying case. So we got 3 is left out, 1 is left out. No other terms will be excluded. Okay, so you have continuous activity on both sides. Okay, and so we have, but now we have with the exclusions in the middle. So we have for the domain, now if I put in order, okay, so for the smallest of values, I have between negative infinity and but not including 1. Then I have those values of x such that 1 is less than x is less than 3. Again, neither value is included, so I maintain the use of parentheses. And for the rest, okay, have those values of x greater than 3. Okay, so the interval notation defining the domain will consist of 3 sections. Okay, all right. Now, for what we have in the case of the second function, okay, so we have g of x is equal to 2x squared all over x plus 5. Okay, so we have a rational expression. Again, no even root radical, and okay, and one might wonder, okay, does having like x to a raised order do anything in terms of any restrictions involved? And the answer to that question is no. Okay, because you don't have an even root radical, but you just have a rational expression, and the restriction is that still the denominator cannot be equal to 0. Okay, so x plus 5 cannot be 0. So you have one excluded value from the domain, and that is going to be at negative 5. Again, negative 5 is excluded. All the other values are in the domain. So for this problem, okay, the domain is going to consist of two separate sections. And for the first case, we have those values of x less than -5, as well as those values of x which will be greater than -5. Okay. Now, for what we have in the case of the third function, okay, so we have h of x, and we have that as the square root of 9 minus 5x. Okay, and in terms of any restrictions, okay, so we now have h of x, okay, in the form of an even root radical. Okay, so in this case, because we have the square root, okay, 9 minus 5x cannot be negative. Now it can be 0 since I have the radical in direct terms, but now if I had 1 over the square root of 9 minus 5x, it would have also imposed that it could not be 0. Okay, so, but it can be 0 or positive. So for 9 minus 5x, let's say it is greater than or equal to 0. And looking at solving for x, so if I get the x term by itself, okay, so I'm going to take 9 away from both sides. So we're going to have that negative 5x is greater than or equal to negative 9. Okay, now I'm looking at going from negative 5x to x. Again, the thing that's oftentimes easy to overlook, again, is whenever you multiply or divide by a negative, you change the direction of the inequality. Okay, so we're transitioning from greater than or equal to less than or equal to. And so in this case, we're going to have that x is less than or equal to, and we have positive over positive, or negative over negative becomes a positive. So you have that x is less than or equal to 9/5. You can also write that as x is less than or equal to 1.8. And in terms of the domain, you can also write that as x is less than or equal to 1.8. Okay. Then just going to mention, okay, so you have for the domain, okay, so you have like, let's kind of give you a visual, so you have 0, 1, and 2. And 9/5 or 1.8 is going to be between 1 and 2 and closer to 2. And with the equal sign, that is going to be included. And everything else is going to be less than. And so we're going to have for the domain, okay, so have one direction inequality. Okay, and we have the continuity, okay, where we have the lower limit, okay, tending to negative infinity, and putting the domain and reading the activity from smallest to largest, or from left to right. So you have going from negative infinity, from negative infinity, and approaching and including 9/5 or 1.8. And with the inclusion of 9/5, okay, so that is going to be in the bracket. Okay. And for what we have in the case, we'll look at this one more. Okay, for average rate of change, again, average rate of change, that's just another way of saying just what the slope is, okay, whenever you're looking at two specified functions on the graph of the function, okay, regardless of whether the function is linear or not. Okay, so we have for number 4, I'm just putting this down, so we have y is equal to f of x is equal to negative 3x squared plus 2x plus 1 okay, and we're going from x equals negative 1 to x is equal to 4. Okay, so just setting things up here. Okay, so we have y is equal to f of x. Again, we have negative 3x squared plus 2x plus 1. Okay, so for what we have at x is equal to negative 1, okay, so we have that y is equal to f of negative 1 so we have 3 times, okay, the square of negative 1 plus 2 times negative 1 plus 1 again, just for following through. Okay, so for the square of a negative is going to be a positive. So you got negative 3 times 1. Now 2 times negative 1 is negative 2. We have followed by the addition of 1. And so we have negative 3 minus 2 is negative 5 plus 1 is equal to negative 4. Now, for what we have in the case of x is equal to 4, okay, so we have that y is equal to f of 4. So we have negative 3 times, okay, the square of 4 plus 2 times 4, okay, plus 1. Again, the square of 4 is going to be 16. So we have negative 3 times 16. 2 times 4 is 8. And by then you can just regard that as adding 9. Okay, so we've got negative 48 plus 8 is negative 40, and then we have plus 1. So we have at negative 39. Okay, so for this part here, okay, for the average rate of change from x equals negative 1 to x is equal to 4, also that is changing over. Where we have going from negative 1, negative 4. Again, we have when x is at 4, okay, the corresponding y value comes out to negative 39. Okay, and for the average rate of change, okay, it's still going to be conceptually slope. Okay, and we're looking at the straight line that connects those 2 points, and the straight line will be referred to as the secant. All right, so you have y of 2 minus y of 1. All over x of 2 minus x of 1. Again, just identifying, okay, what we're going to have for the first and second sets of coordinates. Okay. So in this case, right, so we have for negative 1, negative 4, we'll just have this as the first set. Right. And at the stage of substituting, so for y of 2 minus y of 1, okay, so we'll have negative 39 minus y of 1. So y of 1 we have at negative 4. For x of 2 minus x of 1, so we'll have 4 minus negative 1. And just following through. Okay, so we'll have negative 39 plus 4. All over 4 plus 1. So we have negative 39 plus 4, so this will be negative 35 over 5. and that reduces to -7. All right. So that's going to be the average rate of change between x is equal to -1 and x is equal to 4.